in the beginning, there was game development. Right, so welcome back again to the 2D tutorial. We're working through the 2D tutorial for MonoGame and getting everyone on board. We'll quickly go. We know the schedule. We've got the weekly schedule. We've got the university today, where we're going through the 2D tutorial. And make sure to grab Tom's tutorial stream tomorrow. We're edging closer to the Ultimate 3.8.5 release, and we're also going to do some big news about that in the next open hour. So next week, stay tuned, next Wednesday. And we'll have more details about what you can expect with 3.8.5, because we're stacking a lot up with this release. And there's even some things we're holding back because it's like, no, this is too big. We're going to put it on. But yeah, Tom is. We finished the song implementation for Vulkan and other for DX12, and we're doing some last tweaks and checks. And as soon as our automation is working again, because those in the land of Linux will know that there's not enough wine, or the wine is too fresh. We need some older wine. It's fun. We've got lots of upcoming content. So at the beginning of the stream, I was actually working on this. So the mobile tutorial is almost finished. I had to stop myself and make sure that I had to stop and make sure we get to the stream, but not keep working on the tutorial, else it might have been a lot quieter. And that's shaping up really nice. Then right on the back of that will be the 3D tutorial, going over the whole 3D things. And we've showcased this before, but it's going to be good fun. You'll have to bear with me while I go through the proofing process, which is quite intensive. And being sponsors of MonoGame, everyone gets early access to all of the new content. So the 2D schedule tutorial is already up there. In fact, we can switch. I'm going to switch back to it. There we go. We'll switch over. And there we go. This is the sponsors area. There's preview for everyone who's not currently a sponsor. We've got the advanced 2D schedule tutorial now. We're getting lots of really good feedback about that. And it's certainly by far one of the easiest shader tutorials I've followed. So much fun. I actually remembered I'm terrible with shaders. The math involved, there was so much in there with a lot of cases. But Chris walks you through. This is Chris 2, not Chris 1. A lot of the simple techniques you can use to build up your knowledge gradually, until you get to the later chapters where you're sort of being bombarded with information. But it's good information. And then there's also the snowfall to sample, which in there. But anyway, let's switch over. So we're here to talk about MonoGame with audio descriptions. And obviously MonoGame is the best C# library out there for building games and getting to grips with games. It gives you more of a hands-on with what's in your game. There's no black boxes or hidden things or having to work out how something does it with whatever framework or engine you're doing it with. Everything's open and it's all open source. Oh, this looks good. I don't think our doc site's down. I was just working on the second again. Right, so getting started is as simple as a click. Jump into the first 2D tutorial, which is where we are, and we're all the way down to chapter 12. We start collision again. 12 weeks we're doing this, and we've still got lots more to go. So, collision detection is by far one of the more fun things that I enjoy when it comes to game development, because it's really we get down to the nitty-gritty of what you need, what needs to happen in your game. Generally speaking, if content's moving around the screen or there's user input and you need things to happen when things either collide or something's going to happen. Not for every game. So, for instance, if you're doing like a card game or things like that, the UX handles all the touch points and clickable things that happen. But when we're doing our games where you're looking at bullets bouncing around the screen and whether they're shooting ships down, or with the case of Dungeon Slime where we have the bat bouncing on the screen and we keep it within the bounds of the screen, and also if our erstwhile slime, if it hits the screen, then it's dead. If it bounces around, it hits the bat, then it gobbles it up, and then we move it on and grow, and then we get another slime in there, or another bat in there, and it's a realm of what some see as a complex scenario where it's not. There are several techniques you can learn. It's only when you get to the light zones of 3D, that extra third dimension gives you 6 degrees more of complexity, and you don't require more dedicated elements there. But you don't need a big physics engine. You don't need some complicated mess to manage this, or you. It's very, very simple. And what you're looking down at is sort of a diminishing set of responsibilities when you're working out if something's collided. You start with the most simple, which is like a circle. Is it within this range of between two elements? What if it is? Then in case of is it within the specific region, this box area that the actual sprite's in, and then beyond that, you're then looking at the pixel level. So, is this pixel of this sprite touching this pixel here? And it's not almost never a case where you're going to do the most complex all the time. It's always working down so that your cheapest, fastest iterations are going over all the time, and then only when the bounds are closed in do you start looking at more complex scenarios and trying to work out what's going on. So, let's take a drink. Through this, and Chris One, that is, has done a fantastic job working through all the different kind of simplistic techniques you can apply to collision detection. If you want to go up to something else to handle, like Box 2D and doing lots of different rigid bodies and chains and ropes and things, you can. But understanding the basics and understand what happens behind the scenes and what goes on will give you a better understanding for which way you will implement it in your game. So we have different collision shapes. So we said we got like circles, squares, and down to like the actual individual textures themselves. Implementing those different techniques at different ranges, and also how we handle overlaps and responses. Because even though we're talking about collision detection, this is not always just on about two things that hit each other, something must happen. It may be a case of there's two things that hit each other, I just need to know it's happened so I can do something else. A good example of that is if I approach a door. So if within a range of a door, open the door. I've not hit the door, I'm not got it. The door is magically opening up for me, as if I walked onto the bridge of Star Trek and it's magically appearing, or you go to some kind of automation door. Or in some cases, I've stepped on a tile. I know the character's over the specific tile. Right, go and start this death trap machine so it's going to spurt out fire and death, and let the character worry about it, and then he walks off the tile and stops. But anyway, lots of different things we can do. So, as we drill down into what collision detection is that we're working on the simplest way first down to the most complex. So the most simplest is proximity. Am I anywhere near the thing that's going to have something happen? Whether or not I'm actually on it or just in within range of it. So we talk about a trap, it might be a case of in a certain area of a trap it goes off, or it might need to wait to sit on the actual tile. You choose what that distance is. And the simplest way we can do this is through circles, because as a mathematical form, a circle effectively is from the center of the circle where you're looking for something, is you're looking for a radius from the center to wherever you are. And all that is a simple distance check of a case of, am I this close to this element? Now, you might ask why I can't just use a vector 2. All my positions drawing the screen's a vector 2, so why can't I compare this vector 2 to this vector 2? Well, that's actually more complex because of the math that's involved in doing distance of vectors, which we'll come on to. With a circle, it's a lot simpler. It's a case of, am I within range of this circle? And the circle classes give you the ability to simply detect that distance as we go through. So here we can see here is that, oh, you can barely see this now. So A down here from your elements that you want to see colliding is case of the distance between, you've got the distance between the two circles, and also you've got the distance between two circles together on the things. Simple trigonometry. Although I must admit, my son now does college, and the math he comes back with just blows my mind. This math I can understand. And in MonoGame, we have a simple way of working out in case of like, are you within a certain range of two circles, or even is my position within distance of it? If you wanted to use vectors, we can use this distance squared method, which effectively is working out the range between those two points. So this circle over here with this radius and this position over here with this radius, are they overlapping or intersecting, as it were? Any of those are vector 2. We're actually doing a circle-based collision detection of, have these two radii from your character to the point thing you're going to hit, are they intersecting and overlapping? There is the vector to distance method, which is this is where we talk about this is actually calculating the distance between two specific vectors. But the problem with that is that there's a lot more math involved in actually working out these two independent vectors. Are they actually position rotated and going to be colliding? It's generally more complex. So we use other methods like the distance squares method to actually work this out because it's simpler. When we get down to the next level, we talk about rectangles. Now, rectangles add a little extra bit of complexity because now we've defined a volume. And whether or not one volume is actually overlapping it or intersecting it some part is that effectively you've not got corners to worry about. But also, a circle, if it rotates, it's exactly the same. If you rotate a square, then as you can see here, arguably the dimensions change or how we're doing. So then the math we need to be able to detect is this square that's centered to this square that's offset. Are the points overlapping and intersecting? The math just gets a little bit more complicated. Not much, but when you're working with especially with collision detection, to keep down to the most fastest and simplest way of doing some things, this is just the next order of complexity and gives you more control. I mean, a lot of games I know they simply just do square-based intersection and don't bother with circles because they don't need to. They've not got that many things on the screen. But if you're working on a bullet hell game and there's millions of bullets on the screen, every ounce of performance is important. So MonoGame provides a rectangle struct, which defines arguably a square, even though it's called a rectangle. It can also be, rectangles can be square. There's just different dimensions. And we've got the four edges on the actual square, the actual rectangle itself. So from the bottom length, from a position, you've got the bottom length, the left length, the right, and the top. So we work out the dimensions. And then when we're doing the calculation of our two different rectangles intersecting, effectively what we're doing is comparing the points of each of those two squares. So is the bottom left of one rectangle greater or less than the bottom right of another one? If so, yes, they're overlapping. Sorry, the bottom right. Yes. So are we overlapping at any particular point or corner as they're doing? And Chris has got a nice little diagram showing these different things and looking at basically we're doing these 4 tests. We're testing all 4 corners against its other corresponding corner, another square where we're trying to see if it's overlapping. If it is, and we're looking at is it overlapping on one side, the top side, upside, or across. The trick with this, though, which a lot of people miss, is that what happens when one square is inside another. So by that point, the corners are not overlapping or touching. So we look at this kind of math in this case of like, well, no, none of the conditions are met, but that's because we're completely enveloped. And so you have to watch out for the additional element. So not just as the diagram shows here, so these 2 squares then overlapping. The redstone shows how much we're overlapping. If one is inside of another, arguably nothing's overlapping or nothing's crossing the edges, and you simply have to watch out for those scenarios. Then we go down to the level. Now, we don't really cover this in the course because it's an entire lesson into itself. Simply because once you've got down to the level of working down to the pixel level of is this pixel of this texture overlapping this pixel of this texture, and that's even assuming you're actually using the image. In some cases, what artists will do is they will actually have an invisible, like a sort of line or box of this is the actual collision area. So yes, there's the sprite. There's lots of, this is an animated sprite. The arms are wavering around. We don't care about the arms. Just has the body intersected. So sometimes you can do that through art, so like a hidden area, or more likely what people do is in their code or their assets when they're importing and defining them, they're saying, well, this is my art area, this is my collision area, having custom collision data built in as part of the asset pipeline to define something. And again, it's finding the simplest method forward. And if you don't have any of that, then you're going down to the level of, right, okay, we know it's within the region. We know with the box of this texture is overlapping. Is the wiggly arm of this character overlapping the wiggly arm of this character? In this case, they've started a fight and all hell must break loose. So this comes down to choosing the method of when you're doing collision detection. Personally, I generally do them all, and it's a gradient design of going most simplest to more complex to more complex, if you need it. Some games, like I say, will just use like a middle ground, so that's good enough. I'll just test that for everything. Don't need to worry about all the different levels. There's not that many things on the screen, as with Dungeon Slime, for instance. So Dungeon Slime is just looking at, have these things overlapped in one pass. That's all we care about, and we're not doing some more complex ways of doing this. So it depends on your game, depends on what you need, and depends on the path you want to take. But ultimately, as ever it is, it's up to you and what you want to do. Now, that covers what happens when two things collide. Now, you've got several different things to happen then. Is that and if you're coming from Unity or Unreal, you have what are called collisions and you have what are called triggers. So, and what we define this in MonoGame or game development in general is that we define this as a collision response. So, what do I want to happen when this collision event has occurred? So, my slime has overlapped with my bat. What happens? Is it a case of, do I just need to know it happened? In other words, I'm going to go off and fire off some kind of particle effect in the system, something's to happen, or do I actually need these things to not collide, not overlap, and actually physically stop the interaction? So if we're doing a physical interaction, it's a case of the bat is hitting the outside of the screen, and when that happens, we want it to go off in a different direction. If the slime hits the edge of the screen, then basically that's game over, man. You're dead. Done. Whereas in other cases, in case of something's happening, you'll need to know it happens. But the Dungeon Slime is a lot simpler, so we only care about actually doing physical reactions to these things. Or, actually, no, sorry. In the case of the slime hitting the bat, then what we're doing is reacting to that by basically then killing the bat and growing the slime. So we're taking a response from the interaction and doing something else, as opposed to something just bouncing off the screen. So as a good example of this, in case we take one location, and when it comes to collision detection, you're always doing it at the what happens next kind of approach. There are more advanced techniques where you're doing predictive analysis of not just here I am, here I'm moving here. You're also then worrying about, well, where's it going to be in the next frame, especially for high frequency and fast things. But Dungeon Slime being simple, we're keeping it on the lowest common denominator. So I'm here, I'm going to move here in this next frame. So what's my new position? We're then when defining a rectangle around the two objects. And then we're doing a simple intersection check. So is this rectangle intersecting with this rectangle? If so, then because we're doing like a physical reaction, it's a case of this can't overlap with that because these are two physical block things. So stop. So you can't move. So that way, what effectively is happening is that I'm walking up to the wall. I can't pass through the wall. It's a case of every time I'm trying to move forward, it's stopping it and saying, no, you can't move. You stay where you are. And it's most simplest case. We go into later about what we do about actually reacting or reflecting of that. And let's see. Yeah, which is arguably the same test. Okay. No, it's the same thing. Oh, sorry. No, okay, so that one's this sample is talking about two things together, stopping them interacting, but also we can apply the same for the bounds of the screen. So here, where we've got the rectangle for the actual character, and then we're actually defining a rectangle for the actual screen. Again, the character is inside the screen, so we're not intersecting when we're inside the screen. It always depends upon whether you need to handle that case or not. With screen bounds, you don't care. And we're just simply saying, here's rectangle around the screen, here's rectangle around the character. Is the character then going to bump up to the edge of the screen? And if it is, again, you can't pass beyond the screen. Stay where you are, as it were. I'd say more advanced scenarios, if things are moving fast, there is a possibility that something could actually move beyond the frame. So if you're moving that fast, again, actually, it's an interesting point there, is that if you're moving that fast from frame to frame, so in this frame, I'm here on the wall. But if my speed is greater than I could actually say, right, we'll move here. Okay, I've moved the entire distance from here to here in one frame. Now, this logic wouldn't defend against that. If you're moving that fast and all of your bounds are on the other side of the fence by the next frame, you've not intersected. So those kind of elements and things you have to also take care of. Where sometimes, in case of, if you are going to have a condition of that, again, it's only if your game has this need. If you see a position where collision detection not happening, it's generally speaking because you're moving too fast. So there's my box. I'm at any point of there where I'm moving across. No, I'm intersecting. I can detect it. However, if it's here, one frame, and it's going to be here in another frame, you'll not get this detection. But again, it's only something you need to worry about if that's a concern. And what you generally do with that is that if there is potential going so fast, you might add an additional check to say, well, are you even outside the bounds of the screen? And I mean, some games, what they do as well is that instead of trying to use this method where we just do rectangle on collisions, what they'll simply say is the case of, have you gone beyond have you gone beyond the X point of the furthest point of the screen, or are you trying to go less than the X point of the screen? To keep it simpler. And it all comes again down to personal choice, what you want to do. So that's physical interaction things going to happen. But like I say, you've also got a trigger response. And all this is simply a case of, if something happens, just let me know about it. So have I collected an item? Has my slime entered my bat? If so, I need to know about it so I can go gobble up that bat, and then he's in my belly and he's going down, and the slime grows and moves along, and so another bat then has to join. So from the event of those two things colliding or overlapping, then we've got several events which are essentially occurring within the game to give that element of gameplay. And so I know that's really is, again, see, this is the only difference between the two, is that where one is saying, right, if you're moving, you can't move if you're intersecting. In this case, it's a case of, well, if this thing happens, I need to do something. We're not stopping the actual physical action. It can continue moving on as much like we don't get involved. And I get that. I should reorder this. Okay, so back to the physical interaction. So that's one method. So if one physical element is moving along, it's butting up there and it can't move, great. But what if you wanted to retain its velocity? So if you think like a breakout game, or in fact, bat in this game, it's bouncing on the screen, is that your bat's going along at a certain speed. Now you don't want it to hit the wall and then stop, because that would be rather dull, because then it can swirl around and can try and gobble up the bat. So what you actually want it to be able to do is, at the same angle and speed that it's going in one direction, once it makes the collision, you actually want to say, right, your velocity has changed, so you're now moving off in a different direction, usually in an angle from where it's going. So we worked it out by saying that, so there's the surface that I'm going to hit. We take its normal, or the plane perpendicular to the actual surface itself, and then we're working out, well, what was the angle to the perpendicular from there, and then what's the angle that's equal, just inverse it, so we're doing the angle of this way, as the diagram shows. I do like this diagram, it's very nice. So we can see that we're coming in here. This is from the perpendicular right angle of there. This is the shortest angle of what we've hit it at. Then find, reflect it and turn it by the same angle going off in the other direction. And yeah, Chris, it's almost like creating a mirror. You're mirroring off what happens. And that's as difficult as it has to be. Now, there are other elements to take into account. So some games will have it so the case of there's a surface and it has a level of friction. So something's not just bouncing off it. By the force of the impact, it's actually going to potentially lose some velocity, so it goes away slower. Again, that's usually breakout game things. Or it might even go faster. And that's okay, surfaces that have some kind of physics interaction or physics behavior on a surface. So something to take account of if your game needs that. But at its most simplest case, we've got the bounds of the screen, we've got our bat bouncing around, and then if it hits the corner, then we're working out a case of just not necessarily has it just hit, because we don't want to stop it moving. We want to say, well, if it's hit, how far past the wall would it have moved? If so, then move it in the inverse direction off in the other direction. And that's all the simple math. So we work out how much it's going to have moved off the screen, determine the distance it would be, and then a simpler math then work out based on the direction of its input. We want to then reflect it back out. So we simply do the calculation based upon which, don't forget, the calculation is different based on which wall we're hitting. So if we're hitting the roof, the side, the bottom, or the side, or the left, then it's a slightly different calculation. And then once we've worked it out, the Vector 2 method has this reflect option, which does that. It does the math to effectively calculate this for you. So you know from the normal, you're having a Vector 2 coming in, we're going to reflect it, it's going to give you a Vector 2 off the other way. It does it for you, you don't have to worry about it. You just need to know which way you're going to go. Bear in mind as well, obviously, then you want it to go off at the same velocity and speed that it was going to be at in the first place. There we go, right. It's one of these things where it sounds complex, but MonoGame provides you most of the functionality to do all this for you. And you just need to work out which way direction you want to go, ultimately. And also then if by hitting it, do you actually increase or decrease the velocity that's actually going along? And so forth. And yeah, read the tips. All right, okay, so we've covered all the basics now. So this is a very heavy theory episode, sorry, but it's collision detection. It's worthy knowing the fundamentals and what's going on. So once we've got all those things, again, it comes down to when you're doing your game implementation. Are you doing just a simple check for all elements and doing it the same way, or whether or not you actually need to have levels of collision depending on what you're doing? Ultimately, it just comes down to the performance of your game. And my general feeling is that do it one way. If you start to hit performance issues, implement an additional pre-phase to do pre-checking to ensure that you're cutting down the most expensive calls. If that's still causing influence, implement the next phase. So work on the lowest common denominator. This is what you need to happen. This is the design of your game and what's going to work, and go over. Right. Now, from here, then, we're going to switch over to our code. Okay, there's our lovely project. I shall check. Yes, last week I went and committed in. And you keep in mind from the beginning of this, now we set up a source code repository for all of our code. So all of my code doesn't live on my machine. Anything I change, I make sure I batch up and then I commit and then upload to the server, which is all up to date. And there's our project. And we're going to start our journey off in our library because obviously we're creating constructs which are core to our game, which can be shared anywhere. And in our, what we're going for? I'm going to say our graphics folder. I'm going to create a new class. No, this actually says to create in the root. I want to follow the tutorial as everyone should. So we're going to create a definition of what we class as a circle, which gives an easy way to this. We're going to do circle-based collision through the entire game because that's all we need. We don't need anything more complex. Go soon to find where it is. And we're going to start our circle struct there. As you notice, that straight away, well, we didn't turn off our AI. Go away. Thank you. Straight away, we hit one problem here because we've got a definition. Now, we talked about interfaces in the previous section where we defined an interface to control our own game objects. Same in .NET. .NET also has interfaces for defining contracts for things. So iEquator is an interface. And what this basically says is If you're doing comparing of objects between each other, so I want to compare this object to another, you need to define in your class what that means. So how do I compare this object to this one? How do I say it's not this object? Or in some cases, if this object is greater than this object, what does that mean? And so, I mean, I could just here go implement interface, and then that shows me there that to meet the I-equatable interface, I need to at least say, how do I know that this object is the same as this object, or if it's not? Nice and simple. But anyway, we want to go and create a static. Now we're creating a nice little static accessor here so that it makes it easier to actually define or get access to a circle or define functions which you can access anywhere. And then we're going to have some properties on this class where we need to know obviously the X and Y coordinates of where it is in space. And then more importantly, when it comes to our collision detection, what is the radius? So from the center of this point, how far off is the collision area that this element, the circle, is defining? Then we got some properties. So we want it because we got X and Y in there, but obviously that's just there. But realistically, we're talking about a position or a point in space. Point is also used as a vector too. It's just a different way of describing a point. A vector 2 has other connotations within it because it has distances and it has other elements in. A point is a much more simpler way to say, I want to know something by its X and Y position and nothing else. It's good in programming these things to use the correct kind of data structure to fit what you're doing. So you're trying to keep as memory efficient as possible with all of your data around here. So a point is more memory efficient than trying to use a vector 2 in this case. In other cases, you might want to actually have a vector 2. And point, and then obviously, if we have a circle which is empty, we want to be able to track that to keep it simple. So we're not having to every time to say, has this got no radius? Is it just a point? Then we add math to work that out for us instead of having to have it all the way through our code to work out it's empty. We've got it in the class. It says, I'm empty. Okay, and to help with some of the other elements of when our objects are on the screen, again, to make it easier, we can actually work out what is the topmost bound, the bottom, the left, the rightmost bounds, because obviously then we can treat a circle like a square, but it's still a circle, but we're just giving it square-like properties to help with collision detection and other things like that. And also means that it reduces the math we're going to do because, as you can see here, X plus radius minus Y, where I can just take and say, just circle to the left, right. And as ever, we need a constructor. I'm going to get rid of you for now because we don't need yet. Where if we're creating a new circle, then we can give it a position and a radius, or we can give it a point and a radius. It's the same thing, but we're just populating it from different elements. And then obviously we need to know, I've got two circles. Are they touching each other? Or are they going to touch each other effectively when we're looking at the next round? So here, this is where applying our math from earlier. So from the position it's at, is the square of the radius, so the diameter of our circle, and is that going to collide with another circle? So from this circle, is it going to collide with the other one? And then if it has, or even if it hasn't, what's the distance then between those two circles in space? Right, and that's one thing. Now, if you remember when we implemented the interface for the actual equatable, it only required one. Well, it's actually almost better in a lot of cases to provide more than one. Now, you provide one, which is the interface, which basically says, has this object collided with another object? Which doesn't really help us at all because it could be anything. We need to know, is this object that is a circle colliding with another object, which is a circle? And then if it has, then we can actually say, right, fine, if I'm testing a circle against another circle, this is now how I work out, are they the same circle? So are they at the same position in the X and Y, and is its radius the same? Now, that works for 99% of the time. But what happens in that one unique chance when another circle is actually completely overlapping another? It's not the same circle, but it is at the same position radius. But for the simplistic game that the Dungeon Time is, that's not a scenario that's ever going to happen or worry about. If it is going to happen in your game, then you also need to consider that when you're comparing two different bounding volumes that want to collide. Because if there is the minute chance or possibility where the two could completely overlap, well, you don't want to say it's the same circle, because in that instance it would go, is this circle compared to this circle? No, it's the same one. Okay, ignore it. All such fun things. But these are sort of edge cases. You never need to really worry about these things as such. Not on the element of this. And another feature that's nice to have when you're actually working with iEquatable is to also have the hash code, which gives a unique identity of what is my object. Hashing is just another faster way of saying, if I've got hundreds of these things, another way of saying, are they the same thing? And we create basically a hash code, which is basically, it's just a short form representation of this element, this element, this element, compressed down into a much smaller form, which we can also use a comparison. And then, because we're doing iEquatable, another thing which is nice, so instead of just, formatting. So instead of just doing this circle dot equals, if we also want to be able to say circle equals circle, or circle does not equal circle, then we also provide the additional static operators for those operations. As you can see, it's designated by the operator keyword. It says, if you're comparing me to something else, this is a specific operation that I can apply to compare the two. And if you look at .NET, you'll see these scattered everywhere of simply saying, is this equal to this? So basically, and ironically, all this is doing is saying, does this equal this? It's like a shorthand form version of this and the other. But considering when you work through your code, in most cases, you're saying, is this equal to this one, rather than doing dot equals to that one. It's syntactic sugars, if you were, when you're actually building the code. Okay. And Chris has a nice thing on here where basically it shows you here. So, you go two circles, are they equal? You can, because we've got this equals operator, you can say, does this circle equal this one? But I could also just as simply do dot equals that, and it's the same thing. Anyway, right. Done that, we've done that. Resize my screen. Okay, so there we have it. There we've defined what is our collision object that we're going to use for the game. Quick, restream mods, kill the spammer. I can't do this on my phone for some reason. It's always fun. Kill the spammer. Right. Okay, so we've got our construct, our nice circle in there. Now we need to actually start using it, which effectively is we're going to say that the bat needs its own collision object. We don't need to do one to the screen because we're just going to use the same rectangle bounds for the actual screen dimensions, and then we need to find an object for the actual slime itself. Oh, Harold, Chris, for naming things bat and slime. I don't know why it's a slime. But I digress. So, going over to our game. So that's our library. We've set up our circle. It's in there. We can use it. We go into our game. Always have to keep rewinding my mind back, because at the moment we're still building our game in our game project, and it's still called game. Where generally speaking, when you start building your game out, you'll give it a more unique name, or you'll restructure things out, or you have a library which has your game and your library for your shared code and things like that. But in here, because of so. We need to start properly tracking. Oh, yes. we've already got our slime, and we already control the velocity of that, but also the bat itself is moving on its own. So we need to add I've just noticed an error in the tutorial. There's a line that's not highlighted. Oh no, it is. I'm blind. Okay. So we want to start implementing first our bat, because our bat wants to be able to bounce around the screen happily on its merry way, doing what it likes. So like with the slime, where we need to track its position for controlling from the player's input, so I'm moving it, the bat itself needs to control its own position, but also the speed and the direction it's going. The slime is controlled by the player with its input, but the bat is moving on its own. And then we need to implement or initialize that in our initialize method. So we need to get our bat ready to use. Yes, we've got a handle function we're not implemented yet, but we're going to get to that very shortly. And also in that, but then we need to start working on our actual selection code. Now this is quite a long paste. Let's go all the way up here, and then let's walk through it, because most of this is just implementing what we've just discussed going through the tutorial. So after we've got our bat on the screen and we want it to move, I'll leave it. I'm not going to mess with it. I might put it through on that function later. So we're working out. So for every frame, every update, we're checking the bounds of the screen. You might think you could only do that once, and your screen's never going to change. But the thing you have to remember now, why we do this in updates is actually quite crucial, because especially on Windows or on some of the devices, the screen size can change. Because I might increase the resolution or I might decrease the resolution. If that happens, then this needs to be changed. So this is why when we're looking at bounds of a screen, we always do it every single frame. So what is the size of the screen now? Then it's basing all your calculations on that. If I just initialize this once and then someone resizes the screen, nothing's going to work, or it's still going to work off the original measurements and design. So your game will then stop working. Not good. So every update, if you're working on the bounds of a screen, you're always checking it every single time you're doing an update. There are other ways to do this. There is an event for device resolution changed, affecting an event, which gets fired. So if the dimension of your screen, that's if it's gone full screen, if it's been windowed, then we can react to that and then reinitialize it. But in most cases, this is a very, very low impact check. So all we're doing is a rectangle is a struct, and we're setting up the struct each loop. Very minor, so I wouldn't worry about it. We're then saying, okay, we're going to set up a bounding box for the slime. Now, we'll refactor this later when we talk more about objects for the slime and the bat, and so it can contain its own. What is the simplest way going forward, working on it? We work out where the slime is and how big it is. So we're saying that it's the slime width plus another 50%. So it's not just the slime, it's a little bit bigger. We do a check to say, is the slime near the edge of the screen? And we're going to do something with that information in a bit. Then we calculate the position of the bat. So where is the bat now? So from its current position, we're calculating where the bat's going to be. So we know where it is. The bat is here, and it's going this fast. So I'm going basically in this direction at a factor of 2. So from here, I'm going to work out this is where I'm going to be in the next frame, or in the next update. This update. We then work out, we create a bounding circle for the bat, so that we can calculate from where it's going to be. We do all the collision checks based upon where the bat is going to be, not where it is now. And then we do a check on the edge of the screen for the actual bat to normalize its position. And then If the bat is intersected with the edge of the screen, then we're going to reflect it back off into another direction, and hence then we're going to update the bat position. If it's not, then it's going to keep continuing on its merry way as it likes. Then we're checking if the slime so we're checking if the slime is intersected with the slime is intersected with the actual bat, and if that happens, we're just going to bounce it off in another direction. So it's not eating it yet. We're just going to bounce off. The bat lives another day, and it can go off in its own merry way. But also at the moment, we're missing this one important handy little function, which all we're doing is saying, bat, you're here, go that way. So that when we start, the bat is going to spawn onto the screen at a position. Where are we? There we are. When we start, we're going to basically start it where it is now. We'll click on the screen and then randomly set it off going on its merry way. It will keep going until it hits the edge of the screen and it'll bounce back off. And if it collides with, then down here, if it collides with the actual slime, then it's also going to bounce off the slime and go off another way. It's the invulnerable bat. We give it armor, it's shielded, so it cannot be eaten at this time. So much code, right? And then we need to update how we're drawing the bat. So down here now, so far we're simply drawing the bat. Where are we? Yeah, the bat is simply being drawn in a position to the right of where the slime is. But now we want to say, okay, the bat has got a life of its own. Can you draw the bat where the bat is? So it's going to happily wander around the screen and going off. So, right, we can now should run this, providing I've not broken any code. Again. I'm going to run this now. I'll bring it up on the screen. Where are we going? Which screen are we going to appear on today? We're over here. So there we go. There's our bat. He's happily bouncing off. Fortunately, he's going off in one direction, but if I move my slime, there you go. That must also be altering. Oh, I see. It's also in that assigned velocity. Okay, there I missed that little bit. So let's get rid of view. In this little function here, no, it's not. That's going off and flip. Should only be changing the angle. So something freaky is going on there. Huh. I'll have to investigate that. Because the code says, are we doing something funky down here? We're intersecting. There we go. Missed it. See, it's the simplest things when you're looking at what's going wrong, because yes, we're assigning with velocity, but what we're also saying is that when it collides, then give it another random position. So I missed that. I thought it would just collide with it. But if I don't do this, if I comment that off, then I'll just stop the game, stop you, and we run you on you again. So that does a little bit more than I was anticipating. So, okay. Our batteries haven't gone. Now if I do this, now, ding, there. It's now going to bounce off my slime. It's invulnerable, I can't eat it. But the reason this logic is in here in this way, rather than just that, is that we're going to do more later on. So instead of just, bouncing off, what we're effectively going to do is going to kill that instance of the bat, because the slime's going to eat it, it's going to go off. And effectively by cheating, because we love to cheat, we're simply going to say, right, well, instead of just creating another bat, it's the same bat, and moving on, and just simply say, right, you were drawing here, you've been eaten, go away, and you actually moved over. While this happens, we actually moved the bat over to another place. So that it is actually this. That's something I didn't realize on this tutorial. It's the same bat. We never actually eat the bat. We get close, we chomp our jaws down, but it then teleports itself to a different point of the screen, and it happily goes on its way. But we somehow feed off that portal energy where it's teleported itself, and we grow. Ah, such good fun. How we doing? Hey, look, we're actually in time. I thought we would be over. So, now one thing I wanted to call. Okay, so that's pretty much it for the tutorial for this week. If we go back over here, so in here, effectively, we're tracking the position. Now we're tracking the position of the bat. We're also giving it a random direction or a velocity. A velocity, don't forget, is position plus direction. We randomize that, so it's pixel random way it's going to go, and we're not getting too au fait about how random it needs to be. It's just a random direction, off on the merry way. And then we're testing each frame. Here's where the bat is, and this is its colliding volume. This is the slime. This is its colliding volume. Are they touching? Then we're going to do something else. And additionally, we're testing if the colliding volume of the bat hits the edge of the screen, then it's going to do the redirect and go off as well. Keeping it simple. Yeah, it doesn't need to. It teleports away. I feel lied to now. Oh, okay. Now, one thing I meant to do this earlier, and I was going to call this out, is that for those you not know it, so over in our MonoGame Discord, there's this lovely channel called Tutorials. And there's lots of stuff in there. This is all community level tutorials, not necessarily the MonoGame ones. But of late, there's been some interesting ones turning up. So we talked previously about this 2D warped TF one, which is really fun to work through. Someone else is also doing their own little shader tutorial about learning shaders, which is actually quite fun. Some of the stranger things again. So MonoGame being a C# framework, we're built with anything that can run C#. That includes the likes of F# and even VB or Visual Basic. So if your language of choice is something else, MonoGame will still work, and there's guides and tutorials about showing you how to do this. So this nice tutorial goes up to say, if you want to go all functional, F# is class a functional language. Its language is slightly different, but it's driven around different principles about how you build projects and games. And MonoGame you can use with F#. If you want to do with Visual Basic, I grew up on Visual Basic. But I never choose to go back there. If you like Visual Basic and you want to use MonoGame, you still can. Just because MonoGame is a C# library, it can still be consumed and used by a Visual Basic program. It's just like tweaking sheets. But also, Wacky has also put out what is really good. It's actually poignant for this week's session on collision detection. He's got a nice little math cheat sheet. Let's see, can I get this up? And this is a simple Figma design. As long as it's still live. Come on, Figma. There we go. And this has got simple things of some basic math formulas broken down into MonoGame terms. So there's the math of working at angles, and then it works it out of this is all the actual code of what these mean. So if you're doing a square root, this is what's actually doing. If you're doing a normalize, where you're balancing out the directions of a vector, this is the math, and this is what it's doing. And I found this interesting. It seems to be growing up because they're still doing some more over here. There's some more angles thumbs here. Oh, doing sines and cosines. But and we've also got this lovely section over here of doing matrix multiplication. Everyone's favorite nightmare. That's kept me some sleepless nights. There's next working on the X-main matrix. Working that into the math for how that can be determined, and then examples for how that matrix multiplication works. Highly recommend it. It's all up on the Discord. Well, I thought I'd throw that in. But anyway, thank you for watching the stream. If you're watching offline, then you can make sure you can catch us on the actual chat. Where are we? Yeah. We've got the Discord chat for actually catching up on anything you want to chat about this chapter or any other chapter. Jump in. That's there. Make sure as well that if you're on YouTube, make sure you like and subscribe. Every click helps. And same if you're on Twitch, then make sure you hit that bell and follow MonoGame and get your alert of updates. We're constantly trying to grow the audience for MonoGame and trying to reach out to people. If there's something you want to see and we're not doing yet, or anything you want to get involved, or if there's a simpler question that you want to ask, by all means, jump in. And this has to be the quietest week going, apart from me being muted in the beginning. I've just noticed, yes, I've got lots of notification on Discord to say I was muted. Yes, thank you, Tom. Like Tom, I should keep my Discord on my phone or something on the side, but it's there. So, I'll hold for a few minutes to see if there's any burning questions. We went through a lot today with collision detection. It's one of those. It's always seen as a more complicated subject than it is, and ultimately it just comes down to use what you need. And generally, that's a principle with any game you build. It doesn't matter what some other big projects done, even our samples themselves. Even if they're doing this huge, humongous thing, if that doesn't make sense for your project, your game, don't use it. Work in a simpler way and a much easier way of doing this. You never want to make your project any more complex than it needs to be. Okay, so yep, we're just getting thank yous, no questions. So in that case, I'm going to bid you adieu. I'm going to keep to time for a change, and we shall see you next week for what we're doing next week. What are we doing next week? Next week is next week is tile maps. Now I will stress because the subject of tile maps comes up occasionally. This isn't using tiled. This is just implementing tile maps within our game, doing it in a much simpler way. There are other ways of doing tile maps. I know we'll go over this next week. You can use tools and utilities to design your tiles rather than doing it this way. This is keeping it simple because we're doing entry-level stuff. But anyway, next week looks like it's going to be rather interesting. But anyway, thank you everyone for joining. I shall catch you next week and on with the show.